Thank you, Mr. Chairman. Good afternoon, everyone. So my name is Emmanuel de Clézio, and I'm gonna just check this laser first. I'm gonna talk about the work of our former PhD, who is Pierre-Antoine Meignen, about multi-element transducer dedicated to quantitative acoustic microscopy imaging. I'm from the Institute of Electronics and System down in the south of France, in Montpellier, and the institute is a laboratory of more than 200 researchers dealing with sensors, reliability, infrared, and terahertz. I'm currently the head of a team of more than 20 researchers dealing with material, microsensors, and acoustics. And we deal with the conception, manufacturing, and implementation of sensors, mainly for harsh environment applications and non-destructive evaluation and testing of manufacture and natural meat. What is one of our strengths is that we control the conception of the and manufacturing of the sensors from the material synthesis to the diagnosis. That it doesn't work. And through the integration of the active material in devices. We work on acoustic microscopy. So as you may know, thanks a lot. Acoustic microscope is a high-resolution imaging device that works at frequencies up to the gigahertz to allow resolutions down to the micron or less. And we manufacture our specific acoustic sensors and the electronics to allow the imaging of industrial and biomedical applications. Here you've got an image of our sensors and of an acoustic microscope that we introduced into a joint laboratory, European joint laboratory, next to a nuclear hot cell. So it was designed to perform images of nuclear fuel after combustion. So quite quickly, an acoustic microscope is a device like this, where you see the sensor here, the sample holder with no sample for the moment, two motors to allow the displacement of the sample holder, and this is associated to excitation signal to control the emission of the piezoelectric element here. Motor control, of course, and acquisition, signal processing, and post-processing. The imaging technique is double. You can perform images of the surface of the sample. So here you've got a scheme of the sensor with a piezoelectric element that is deposited onto silica dilly line, at the end of which you have a lens, acoustic lens, that will focus through the coupling medium the acoustic beam onto the surface of the sample. So when you move this the sample, for example, with respect to the sensor, then you can dot by dot reconstruct an image of the reflectivity of the sample. Then, if you lower the sample, you can focus the acoustic beam in the depth of the material to have an image of this depth, or you can also work on the characterization. The first two imaging protocols were made to control the material to see if there is any difference or any defect. Here, if you lower and if you are able to generate a surface wave, because the angular spectrum of the acoustic beams includes the Rayleigh wave angle, then you're able to generate surface waves at the surface of the sample, and this surface wave will propagate along the surface and will be received back by the piezoelectric element. And this signal reception will interfere with the specular wave. And what you obtain if you if you acquire the signals at different positions, vertical positions of the sensor, then you have this kind of curve. This kind of curve is called an acoustic signature, and in fact, it's an interference pattern that is linked to the wavelength of the Rayleigh wave at the surface of the material. And this wavelength, or this Rayleigh velocity, is linked to the longitudinal and transverse velocity, and is also linked through these equations to the Poisson ratio or the Young modulus of the material. It means that by acquiring for a single point, acquiring a vertical a series of signals acquired at the vertical positions of the sample, then you are able to have the Poisson ratio or the Young modulus local property of the material. So the thing is that to perform an acoustic signature, I've already said, you need a 1D acquisition, in fact, of signals. So if you want to perform an image of the local properties of the material, then you'll need to have a 3D acquisition system. And it's much too time-consuming to allow currently the acquisition of the image. So the objective of the project, of the Pierre-Antoine project, was to propose a multi-element design sensor to limit the number of acquisitions and to allow quantitative imaging of properties of material at the Meignen scale. So what he first proposed was to perform this kind of design, and the prototype that we will deal with today is, for the moment, working at 10 megahertz. So it's the first prototype, and we'll increase the frequencies in the next future. So it's made of a lithium niobide piezoelectric element that is metallized to have form the electrode. It is mechanically drilled, and it is made of one central element and two pairs of lateral elements. These elements will radiate differently into, here you've got an image of the radiation field in the silica Delaunay for the central element. So you see a collimated field that will insonify the lens, acoustic lens, here at its center. So this field is being radiated into the coupling medium and is focused down to, let's say, at position at between 5 and 6 millimeter away from the sensor. The lateral electrode, then you see here again in the Delaunay, silica Delaunay, you've got the collimated acoustic field, and it insonifies a region on the border of the acoustic lens here that includes the Rayleigh angle propagation. The focusing areas is situated again between 5 and 6. So you can here mix the two waves or not by switching the connection, saying I'm acquiring just the central one or the lateral paths. So what we did is, first we tried to validate our method by proposing a protocol to allow the imaging of the material properties with only two acquisitions. So here you've got the acoustic signals that were received on a silica sample, that is a highly homogeneous sample, at two different vertical positions of the sensor. And by this simple equation linking the vertical distance between the two positions and the time delay between the two samples, then we can reconstruct or recompute the Rayleigh velocity. And here is an image, so 10 by 10 millimeters, and with a resolution of 25 micrometers, meaning that we've got 400 pixels here, an image of the Rayleigh velocity of the silica. The velocity range is between 300 and 3,300 and 3,350. So it's really highly homogeneous. So this was, and of course, in accordance with the value from the literature. So this was the validation of our protocol, and we applied it to a chromium sample. So the image is less, how can I say that? Maybe less elegant, but in fact it reflects the heterogeneity of the chromium sample and the anisotropy of this sample. Again, it's a 10 by 10 millimeter squared image with a 25 resolution, and it's the first image, quantitative image of here it's the Young modulus of the chromium sample. Sorry, it's the quantitative evolution imaging. Sorry. Each color corresponding to a value of the Young modulus. So to conclude, we proposed a multi-element sensor with 2 pairs of lateral electrodes and 1 central electrode to allow the separate the generation and reception of the specular wave and the surface Rayleigh wave. This allows the material characterization and imaging thanks to only 2 set acquisitions, so that reduces greatly the time of reconstruction of the image. And this was validated on silica and first applied to the characterization of chromium sample. In the near future, we would like to increase, thanks to clean room facilities that we have in the lab, to increase the resolution by increasing the frequency of the sample and going to frequencies over the hundreds of megahertz. And because we have 2 pairs of lateral electrodes, then we'll be able to scan to image the sample in 2 orthogonal directions, namely investigate the anisotropy of the material. Thank you.